Alright, in this section here we're going to be talking about concavity and points of inflection. So we're still analyzing the graphs of these functions here. This particular one we're talking about is x squared plus 1. So this is the graph here of x squared plus 1. And we talked about earlier that to find the minimum on the graph, and that would be about right here. Okay. In this particular section here, we're going to be talking about concavity. And I'm just going to tell you here that as you can see the graph, it's concave up. Okay, so I think after I work a few examples, you'll be able to look at a graph and tell whether it's concave up or not. But pretend that this is like a cup and it holds water. Okay, pretend it's a cup and it holds water. So if it holds water, we can say then that it's concave up. Alright, well, let's figure out how to determine this, and so let's go to the whiteboard. Alright, so first thing I'm going to do, of course, is let's write out that function f of x is equal to, and that was x squared plus 1. Okay, so to find the minimal point on the graph, we took the derivative, the first derivative, we set it equal to 0, and we got our critical numbers, and we plugged those critical numbers back into our function to actually find the point on that graph. And I'll just kind of sketch the graph out right here, which was, right, this particular graph, the minimal points here. But to find the actual concavity, what we want to do, and the inflection points, what we're going to want to do here is we want to take the second derivative. So we're going to take the derivative of the derivative. So the derivative of 2x is just 2. And then what you do is you set this equal to 0 and solve for x. Well, there are no critical numbers here. In other words, there's not a number that we can plug into this to get 0. Okay? So no matter what number we plug in, f double prime, for example, if we were to plug in negative 10 into this, we still get 2 out. And 2 is a positive number. Okay, so if you looked at this as like on a number line, no matter what number we picked on the number line and we plugged into our function, we always get a positive number out. So no matter what it is, we're always going to get a positive number no matter what number we choose on the number line. And we could say then that this graph is concave up. Now you notice this line I'm using here, it's it's not a straight line where I used straight lines to determine if the graph was increasing or decreasing. I use these concave type lines here to determine whether the graph is concave up or down. So in this particular case, okay, we don't have any inflection points. But we can say that the graph is concave up, and I'm just going to label it as CU here, is concave up from negative infinity to positive infinity. Okay, well, let's look at another one. So in this one here that I'm about to write up, I don't know, we'll call the function r. How's that? So this is going to have all kinds of stuff. We got x cubed minus 6x squared plus 12x. So the first thing I'm going to do is I'm going to take the first derivative, r prime of x, gives us 3x squared minus 12x, and then plus 12. And then I'm going to go ahead and take the second derivative. Wow, that's an r, didn't look anything like that one, but whatever. So we end up with 6x minus 12. We're taking the second derivative, we're setting it equal to 0, and we're going to get these critical numbers. Alright, we set it equal to 0 and then find the solution to this equation here, which is going to end up being 2. So, alright, this is the solution. Okay, when x is 2, we plug that in, we get 12, and 12 minus 12 is 0. Alright, so that's going to be our key number right there.